In every atom, in every star, in your own body right now, trillions of tiny points are spinning with no size at all. Physicists call it the electron. Simple to draw, impossible to explain. It can be two places at once, vanish behind a fog of ghost particles, and split into a mirror twin that erases it on contact. Today we chase this puzzle to the edge of what science understands, into a particle that may hide inside a black hole, a magnetism number so precise it took a fortune to measure, and a stillness that secretly trembles. If a tiny mystery like this pulls you in, tap subscribe. It helps this channel grow. Take a breath. Hold on tight. We begin. Picture the smallest speck you can imagine, then shrink it until nothing is left. That empty spot is close to how physicists describe an electron. Every test ever run points to the same strange fact. The electron shows no size, no width, no edge, no surface for anything to bounce off of. It behaves like a location in space rather than an object sitting inside that space. Everything around you takes up room. A grain of sand takes up room. Even a single water molecule has a width a lab can measure. The electron breaks that pattern. Scientists have slammed beams of energy into electrons using machines built to catch the smallest possible structure. Every result comes back blank. No shape, no inside, no boundary to find. Try this picture. A friend hands you a baseball and swears it weighs the same as a normal baseball, spins the same, has the same charge running through it, yet has no size whatsoever. You could never touch it, because touching needs a surface, and this object has none. Strange as that sounds, it is close to how modern physics treats the electron. For most of history, scientists assumed every object, no matter how small, had some shape hiding inside it if you zoomed in far enough. Atoms were once believed to be solid balls. Then scientists cracked them open and found smaller pieces inside. Protons and neutrons looked solid too, until scientists found even smaller pieces called quarks swimming inside them. Naturally, everyone expected the same pattern to repeat with the electron. Zoom in far enough, and something smaller should appear. It never did. Every experiment designed to find a smaller piece inside the electron has failed. Physicists pushed their machines further and further, smashing electrons together at speeds close to the speed of light, hoping a crack would show. The electron held its shape as a single point every time. A 15-year-old staring at a soccer ball can picture shrinking it down to a marble, then a grain of sand, then a speck of dust too small to see. At some point, your brain wants to stop and say that speck still has some tiny size left, even if it is impossibly small. The electron refuses that final step. Physics currently treats it as having exactly zero size, not almost zero, not too small to measure, but mathematically zero. That single fact breaks some of the deepest equations in physics. A few of those equations predict impossible answers when you plug in a size of zero, answers involving infinite energy packed into a single spot. Scientists have spent nearly a century patching around that problem, and we will get to the patch soon. For now, hold this thought. A point with no size at all somehow carries real weight, real charge, and real motion. That single point does something even stranger than existing without size. It builds every atom in your body and every atom in every star above you, and that is where the story goes next. Every atom in existence needs an electron to hold itself together. Strip the electrons away from any atom, and you are left with a bare nucleus, a lonely clump of protons and neutrons with no chemistry, no bonding, and no way to form anything you recognize as matter. The electron, this point with no measurable size, is the piece that makes atoms behave like atoms. Think about your phone screen for a second. Every pixel lighting up right now depends on electrons moving through tiny circuits. Every spark of static electricity you feel after walking across a carpet is a stream of electrons jumping from your skin to a doorknob. Every color you see is light bouncing off electrons as they shift between different energy levels inside atoms. Remove electrons from the picture, and none of that happens. Here is the part that should feel impossible. A single hydrogen atom, the simplest atom in the universe, is built from one proton and one electron. The proton is roughly 2,000 times heavier than the electron, yet the electron is the piece controlling almost everything about how that atom behaves chemically. Size has nothing to do with influence here. A point with zero size is steering the behaviour of matter that outweighs it by thousands of times. Zoom out to your own body. A 15-year-old weighs roughly the same as a large dog, and nearly all of that weight comes from protons and neutrons packed into the nuclei of trillions of atoms. Yet none of the chemical reactions that keep you alive, digesting food, breathing air, firing signals through your brain, could happen without electrons darting between atoms, forming bonds, breaking them, and forming new ones. The heavy part of you sits still. The nearly weightless part does almost all the work. Scientists sometimes compare an atom to an empty stadium with a marble sitting at the centre, representing the tiny, heavy nucleus. The electrons, by comparison, are more like a hum of energy filling the empty stands, present everywhere in that vast space at once, rather than sitting in one fixed seat. That image helps explain why atoms take up so much room compared to the tiny nucleus buried inside them, and why the electron cloud, not the nucleus, decides how one atom bonds with another. This raises an obvious question. If the electron has no size, how does it manage to fill a cloud that large, spread across the space around a nucleus like a stadium full of static? The honest answer is that nobody fully agrees on what an electron looks like while it does this. Some physicists describe it as a wave stretched across the whole space. Others describe it as a particle whose location stays genuinely uncertain until measured. That single question, wave or particle, has confused physicists for over a century, and untangling it is about to get stranger, because before we reach that fight there is another impossible fact waiting. Every electron in the universe, in your body, in a star 8,000 light years away, is exactly, perfectly identical, and nobody can fully explain why. Pick any electron in the universe, pull one from a distant star, one from your own fingertip, and one from inside a lightning bolt striking the ground somewhere in Texas. Compare their charge, their weight, and their behaviour side by side. Every single measurement will match exactly, not close, not almost identical, exactly the same, down to the most sensitive digit any lab has ever produced. That fact sounds obvious at first. Of course, electrons match each other, they are all electrons, but compare that to nearly everything else you know. No two snowflakes match perfectly, no two fingerprints match perfectly. Even factory-made items stamped out by the same machine carry tiny differences if you zoom in with a strong enough microscope. Nature almost never produces perfect copies of anything, except, somehow, the electron. Physicist Richard Feynman once wondered whether every electron in the universe might actually be the exact same electron, bouncing backward and forward through time so many times that it appears in trillions of places at once. That idea sounds like pure imagination, and it never became an accepted explanation, but it captures how strange this perfect sameness felt even to one of the greatest minds in physics. Here is a comparison a 15-year-old can picture clearly. Imagine a factory that has produced every basketball ever used in every game across the entire planet, and every single ball came out with the exact same weight, the exact same bounce, and the exact same size, without a single flaw. Ever, across billions of basketballs. No factory on Earth could pull that off. Yet nature has done exactly that with electrons, trillions upon trillions of them, scattered across every galaxy scientists can observe. This perfect sameness is not just a curiosity, it is the reason chemistry works the same way everywhere in the universe. If electrons varied slightly from atom to atom, or from planet to planet, chemical bonds would behave unpredictably, and molecules as basic as water might form differently depending on where you tested them. Instead, water behaves the same way on Earth as it would on a planet circling a star on the far side of the galaxy, because the electrons building those water molecules are identical no matter where they sit. Physics currently treats this sameness as a basic fact of nature, rather than something with a deeper explanation. Electrons are what scientists call fundamental, meaning as far as every experiment can tell, they are not built from smaller ingredients that could vary slightly between batches. There is no factory floor, no assembly process, and no raw material that could introduce variation, because there appears to be nothing underneath the electron at all. That perfect sameness carries a strange side effect that shapes literally everything solid you touch. Because every electron is identical, nature had to invent a strict rule preventing them from piling on top of each other inside an atom. Without that rule, atoms would collapse inward, and every solid object around you, your desk, your phone, your own bones, would crush down into an impossibly dense blur. That rule is coming next, and it is one of the strangest laws in all of physics. Right now, you are sitting on something solid, a chair, a couch, a bed. That solid feeling comes from a rule most people have never heard of, a rule that says no two electrons are ever allowed to occupy the exact same state in the exact same place at the exact same time. Physicists call it the exclusion principle, but the plain version is simpler. Electrons refuse to share. Without this rule, atoms would not behave like tiny solar systems with electrons spread across different levels. Every electron in an atom would collapse down into the lowest possible level, piling on top of each other like too many people crammed into a single elevator. Instead, electrons stack upward, level by level, each one forced to find a spot nobody else is occupying. That stacking pattern is the entire reason atoms build the wide variety of elements filling the periodic table, from lightweight helium to heavy gold. This rule is also the actual reason solid objects feel solid. When you press your hand against a table, your hand never truly touches the table at the atomic level. The electrons in the atoms of your hand and the electrons in the atoms of the table refuse to occupy the same space, so they push against each other instead, creating the resistance you feel as solidity. You have never technically touched anything in your entire life. You have only ever felt electrons refusing to share space with other electrons. A comparison a 15-year-old can picture clearly involves a crowded school hallway between classes. Imagine a rule forcing every single student into a different exact spot on the floor, with zero overlap allowed, ever. Students would spread out across every inch of available hallway rather than clumping together in one corner. That spreading is roughly what electrons do inside an atom, and it is why atoms take up real space, instead of collapsing into an infinitely small dot. This rule reaches even further than ordinary chemistry. Deep inside a dying star, this same stubborn refusal to share space becomes the only force strong enough to stop a stellar corpse from crushing itself out of existence under its own gravity. We will return to that extreme version later, because it involves electrons holding up an object the size of Earth against a collapse that should be unstoppable. For now, the strange part worth sitting with is this. Nothing forces electrons to follow this rule the way gravity forces objects to fall. There is no wall, no barrier, and no physical object keeping electrons apart. It appears to be a built-in property of identical particles like electrons, tied to a deeper mathematical pattern in how the universe allows matter to exist. Scientists can describe the rule with total precision and predict its effects perfectly. Yet the underlying reason electrons behave this way remains tied to one of the strangest features of quantum physics, a feature about to make the electron look even less like a normal object. Because before we ask why electrons refuse to share space, we have to ask an even bigger question. What exactly is an electron sharing spaces in the first place, a particle or a wave? Ask a physicist whether an electron is a particle or a wave, and you will get an answer that sounds like a dodge. It behaves like both, depending entirely on how you choose to look at it. That is not a joke or a simplification for beginners. It is the honest, tested, repeatedly confirmed answer, and it breaks the basic assumption most people carry about how objects work. A baseball is a particle. It has one location at any given moment, follows one path through the air, and lands in exactly one spot. A ripple spreading across a pond is a wave. It has no single location, spreads outward in every direction, and can pass through two gaps at once, forming patterns where different ripples overlap and combine. Everyday life trains your brain to sort everything into one category or the other. The electron refuses that sorting. Fire electrons one at a time toward a detector, and each one lands in a single, sharp spot, exactly the way a tiny particle would behave. That single spot looks completely ordinary, like a pebble hitting a wall. but send many electrons through that same setup, one after another, and the pattern building up across the detector over time looks nothing like scattered pebbles. It looks like the overlapping ripple pattern a wave would create, with bands of electrons landing frequently in some spots and almost never in others. Here is a comparison worth picturing clearly. Imagine throwing basketballs one at a time through 2 open doorways into a gym, and instead of landing in 2 simple piles beneath each doorway, the balls slowly build up a striped pattern across the gym floor, as if each basketball had somehow passed through both doorways at once and interfered with itself on the way through. That is roughly the behaviour physicists were forced to accept about electrons, and it does not happen with actual basketballs, only with electrons and other quantum particles. This duality is not a temporary confusion waiting for a better microscope to fix it. It has held up under nearly a century of increasingly precise experiments. The electron is best described using a mathematical wave that spreads probability across space, telling you where the electron is likely to be found if you decide to check, rather than telling you exactly where it sits before you look. That wave is not a wave of physical material spreading out, but a wave of possibility, a genuinely strange concept that has no clean comparison in ordinary experience. Physicists confirm this dual nature is a real, tested feature of nature, not a guess. What remains a mystery is why nature works this way at the deepest level, and what actually happens to that wave of possibility the instant someone decides to measure it. That mystery becomes impossible to ignore in the most famous experiment in the history of physics, an experiment so strange that Richard Feynman once said it contains the heart of quantum mechanics inside it, and 1 electron at a time, it is about to prove that a single tiny point can pass through 2 separate openings simultaneously. Set up 2 narrow slits side by side, cut into a solid barrier, with a detector screen placed behind them. Fire a stream of electrons at the barrier, 1 electron at a time, slow enough that only 1 electron exists in the entire apparatus at any given moment. Common sense says each electron should pass through 1 slit or the other, landing directly behind whichever slit it entered, building up 2 simple clumps on the detector screen over time. That is not what happens. Instead, the electrons build up a striped pattern across the entire screen, bands of high electron activity separated by bands where almost no electrons land at all. That striped pattern is called an interference pattern, and it only forms when something is overlapping and combining with itself on the way through. The exact signature a wave produces when it splits, passes through 2 gaps, and recombines on the other side. Here is the part that turns this experiment from strange into genuinely shocking. Even though only 1 electron travels through the apparatus at a time, with no other electron anywhere nearby to interfere with, the striped pattern still builds up after enough electrons pass through one by one. Somehow, a single electron behaves as though it passed through both slits simultaneously and interfered with itself, a behavior with no equivalent anywhere in ordinary experience. Picture rolling a single marble toward 2 open doorways in a wall, one at a time, waiting minutes between each roll so only 1 marble is ever in motion. No sane prediction says those marbles should build up a striped pattern on the far side. Marbles go through 1 doorway or the other, plain and simple. Electrons apparently do not follow that same plain logic, and for nearly a century, nobody has produced a satisfying explanation for why. Physicists have run this test with electrons fired individually across huge gaps of time between each one, ruling out any interaction between separate electrons. They have run it with larger particles too, including entire molecules made of dozens of atoms, and the striped pattern still appears, suggesting this strange behavior is not unique to electrons, but might apply to anything small enough and isolated carefully enough. This experiment is confirmed, repeated in labs across the world, and considered one of the most solid results in all of physics. What remains genuinely mysterious is the deeper meaning behind it. Does the electron somehow explore both paths at once, as a spread-out wave of possibility, only becoming a single sharp particle the instant it lands on the screen? Or is there some hidden mechanism guiding it that nobody has detected yet? There is one more twist buried inside this experiment, and it might be the strangest part of the entire story. If you set up a tiny detector at one of the slits, just to check which slit each electron actually passes through, the striped pattern vanishes instantly, replaced by the 2 simple clumps common sense expected in the first place. The simple act of watching changes the outcome. Nobody has fully explained why looking at something as small as an electron can alter its behaviour so completely, and that mystery is exactly where this story goes next. Add a single detector to the double-slit experiment, positioned right at one of the two openings, with the sole job of recording which slit each electron passes through. The instant that detector switches on, the striped interference pattern on the screen behind it disappears completely. The electrons stop behaving like an overlapping wave and start behaving like ordinary particles, landing in two simple clumps exactly where common sense expected all along. Nothing about the electron itself changed. Its charge stayed the same, its weight stayed the same, its speed through the apparatus stayed the same. The only difference was information, a simple record of which path the electron took. Somehow, the mere existence of that information was enough to collapse the strange wave behaviour down into ordinary particle behaviour, as if the electron could sense it was being tracked. Physicists describe this as the wave function collapsing. Before measurement, an electron is best described by a spread-out wave of possibility, covering every path it could take simultaneously. The moment a measurement pins down real information about the electron, like which slit it passed through, that spread-out wave snaps down into a single definite outcome. The tricky part is that nobody agrees on what physically happens during that snap, or whether anything physically happens at all. Picture flipping a coin and slapping it down onto the back of your hand without looking. In one sense, the coin already landed on heads or tails, you simply have not looked yet. Quantum physics suggests something stranger might be happening with the electron, closer to the coin genuinely being a shifting blend of heads and tails at once, only settling into one real outcome the moment someone actually looks. That comparison is imperfect, since a coin under your hand is secretly already settled, but it captures the flavour of how strange this collapse feels. Some physicists argue that observation only means physical interaction, not human awareness. The detector itself, a piece of equipment bouncing particles of light off the electron to record its path, physically disturbs the electron enough to destroy the delicate overlap needed for the striped pattern to form. Under this explanation, nothing mystical is happening, just an unavoidable side effect of measuring something as small and delicate as an electron. Other physicists push further, arguing that the very act of information becoming knowable, even without a direct physical disturbance, is enough to trigger the collapse. Experiments have been designed specifically to test this idea, gently marking which path an electron took using barely any physical disturbance, and the striped pattern still weakens or disappears once that path information exists somewhere in the universe. This debate remains genuinely unresolved among physicists today. Everyone agrees on what the experiments show. Nobody fully agrees on what those results mean about reality underneath the measurements. That disagreement gets pushed even further by an experiment so strange, it seems to let scientists change the past of a single electron after it has already been detected, and that impossible-sounding claim is exactly where we head next. Take the double-slit experiment and add one final twist. Instead of deciding whether to measure which slit the electron passed through before it reaches the screen, delay that decision until after the electron has already passed through the slits, sometimes only switching on the measurement at the very last possible instant before the electron lands. Physicists call this the delayed choice experiment, and the results seem to defy ordinary cause and effect. If a scientist chooses at that final delayed moment to measure which path the electron took, the electron behaves as though it travelled through a single slit the entire time, producing the simple clump pattern. If the scientist instead chooses, at that same final moment, not to measure the path, the electron behaves as though it travelled through both slits at once, producing the striped interference pattern. The choice made after the electron already passed through the slits appears to decide how the electron behaved before that choice was ever made. Physicist John Wheeler proposed this experiment as a thought exercise decades before the technology existed to actually run it. Later experiments using real photons and electrons confirmed the strange prediction held up under laboratory conditions. The results are considered solid and repeatable. The interpretation of what those results actually mean about time and cause and effect remains one of the most debated topics in modern physics. A comparison worth picturing, while admitting it stretches the truth to make the idea graspable, involves a school hallway camera. Imagine walking down that hallway earlier today, and later tonight, someone decides whether to check the camera footage from that walk. According to ordinary logic, checking the footage later cannot possibly change how you actually walked down the hallway earlier. The delayed choice experiment suggests something closer to the opposite happening at the quantum level, where the later decision to check seems tied to which version of events becomes real. Most physicists are careful to point out that this experiment does not actually let anyone send information backward in time or alter a fixed past in any usable way. No message can be sent to the past using this effect, and no scientist has ever managed to change a historical event using it. The strangeness lives entirely in how physicists must describe what the electron was doing before it was measured, not in any literal rewriting of history. One leading explanation suggests that asking what the electron was doing before measurement is itself the wrong question, since the electron may not have a definite path at all until a measurement forces one into existence, regardless of when that measurement happens. Under this view, nothing about the past actually changes, because there was no single definite past behaviour to begin with, until the measurement created one. This debate remains unresolved among working physicists, and it sits right at the edge of what current experiments can test. There is another mystery lurking underneath all of this, buried inside the electron's own equations rather than inside any experiment, a mystery involving a number that refuses to behave, spiralling upward toward infinity the moment physicists try to calculate the electron's own energy. Every electron carries an electric charge, and charged objects create a field around themselves. Physicists tried calculating how much energy is stored in an electron's own electric field, expecting a small, sensible number given how tiny the electron appears to be. Instead, the math produced an answer that keeps climbing without ever settling down, an answer that technically reaches infinity if the electron truly has zero size. Here is why the size problem matters so much. An electric field grows stronger the closer you get to its source. Around an object with some real width, that growing strength eventually stops, because you cannot get closer than the object's own surface. Around a point with zero size, there is no surface to stop you. You can always imagine getting infinitely close, and the field strength climbs without any limit, pushing the calculated energy toward an impossible, infinite value. This problem sounds like a strange technical detail, but it strikes at something basic. Energy is directly tied to mass, the same relationship packed into Einstein's most famous equation. If an electron's own field carries infinite energy, that suggests the electron should have infinite mass. Every scale in every physics lab on Earth disagrees completely, measuring the electron's mass as an extremely small, perfectly ordinary number. Physics was left holding two contradicting results side by side, one from pure theory, one from every real measurement ever taken. A comparison worth picturing involves an old-fashioned bathroom scale. Imagine a scale that, according to the math describing how it should work, ought to display an impossibly enormous number the instant anything at all touches it. Yet every single time you step on it, it displays your actual ordinary weight without fail. That contradiction, a theory predicting an impossible result, while reality consistently delivers a sensible one, is roughly the situation physicists faced with the electron's own energy. For decades, this contradiction sat unresolved, a genuine crack running through one of physics' most successful frameworks. It was not a minor rounding error or a mistake in a single scientist's calculation. Multiple independent approaches to the math kept arriving at the same broken, infinite result, suggesting something deeper was missing from how physicists understood particles like the electron at extremely small distances. Eventually, a group of physicists found a mathematical trick clever enough to tame this infinity, allowing calculations involving electrons to produce sensible, testable predictions instead of impossible ones. That trick did not explain away the infinity or prove it was never really there. It found a way to work around it, carefully enough that the resulting predictions turned out to match real experiments with almost unbelievable precision. That trick reshaped modern physics, and it came with a strange cost that some physicists still find deeply unsatisfying. A cost involving hidden infinities swept quietly out of sight, rather than genuinely solved. Understanding exactly how that trick works, and why some of the greatest minds in physics have called it more of a clever dodge than a true explanation, is where the story turns next. physicists needed a way to calculate real, usable predictions about electrons without their equations collapsing into infinite meaningless answers. The solution they eventually developed is called renormalization, a name that sounds intimidating but hides a fairly simple core idea. Instead of trying to calculate an electron's true raw mass and charge from scratch, physicists start with the actual measured mass and charge taken directly from experiments, then build their equations around those real, finite numbers. Here is a comparison that captures the basic trick. Imagine you're baking a cake, and the recipe calls for measuring flour using a scale that malfunctions and displays an infinite reading every time flour touches it. Instead of trying to fix the broken scale, you simply weigh the finished cake afterward and work backward, adjusting your recipe until the final result matches the real cake sitting in front of you. Renormalization works in a similar spirit, sidestepping a broken calculation by anchoring everything to the real, measured result instead. This approach might sound like physicists simply avoided the problem rather than solving it, and that criticism has real weight behind it. Even physicists who helped develop renormalization express serious discomfort with it. Richard Feynman, one of the key scientists behind this technique, later admitted that the method felt more like a trick for hiding infinities than a genuine explanation, describing it as something that left him uneasy despite how well it worked in practice. Here is why physicists kept using it anyway, despite that discomfort. The predictions built using renormalization turned out to match real experimental measurements with staggering accuracy, correct to numerous decimal places, a level of precision almost unmatched anywhere else in science. A method that consistently produces answers matching reality that precisely is difficult to throw away, even while the deeper meaning behind why it works remains philosophically uncomfortable for many physicists. Picture a shortcut that consistently gets you to school exactly on time, every single day for years, even though nobody can fully explain why the shortcut works or what strange feature of your neighborhood makes it so reliable. You would likely keep using it, trusting the result even without fully understanding the mechanism behind it. Renormalization occupies a similar spot inside physics, trusted deeply because of its results, while its deeper justification remains debated. Some physicists now view the infinities as a signal rather than a flaw, a sign that the equations describing electrons are being pushed to work at distances far smaller than where they were ever meant to apply. Under this view, a more complete theory of nature, one that fully accounts for extremely small distances, might replace these infinities with sensible finite answers naturally, without needing any mathematical workaround at all. Nobody has built that complete theory yet. This entire mess around infinite energy connects to a genuinely real and measurable phenomenon hiding around every single electron, a phenomenon involving a swarm of temporary, flickering particles surrounding the electron at every moment, popping into existence out of seemingly nothing and vanishing just as fast. That flickering cloud is not a theoretical patch invented to solve a math problem. It has been directly measured, and it is about to explain why the electron's magnetism does not match the simplest prediction ever made about it. Empty space is not actually empty. According to quantum physics, even a perfect vacuum, stripped of all matter and all light, still seethes with activity at the smallest scales. Pairs of particles, one made of matter and one made of antimatter, constantly flicker into existence out of seemingly nothing, exist for an impossibly brief instant, and then collide with each other and vanish, as if they were never there at all. These flickering pairs are called virtual particles, and they are not a wild guess dreamed up to sound dramatic. Their effects have been measured directly in careful laboratory experiments, confirming that this constant flickering activity is a real, physical feature of empty space itself, not just a mathematical convenience. Every electron sits inside a constant storm of this flickering activity. Virtual particles pop into existence around the electron, briefly interact with it, and vanish again, over and over, endlessly, every single moment the electron exists. Physicists describe this as the electron being surrounded by a cloud, though calling it a cloud undersells how violent and constant this flickering activity actually is at the smallest possible scale. A comparison worth picturing involves standing in the middle of a crowded room where people are constantly appearing out of thin air right next to you, brushing against your shoulder for a split second, and then vanishing just as suddenly, over and over, non-stop, for as long as you stand there. That chaotic, constant brushing is roughly what an electron experiences from this cloud of flickering virtual particles surrounding it at every instant. This flickering cloud is not just a strange curiosity sitting quietly in the background. It actually changes how the electron behaves in small, precisely measurable ways. The virtual particles constantly interacting with the electron slightly shield and distort its electric charge and its magnetic behavior, nudging its properties away from the simplest, cleanest predictions physicists would otherwise expect from a bare, isolated electron sitting alone in empty space. Physicists have confirmed this shielding effect through extremely careful experiments, showing that an electron's true effective charge actually appears to change slightly, depending on how closely you examine it, because getting closer means punching through more of that surrounding cloud of virtual particles before reaching what might be considered the electron's true raw properties underneath. This constant flickering storm surrounding every electron in existence leads directly to one of the most precisely tested numbers in all of science. A tiny mismatch between how strongly physicists expected an electron's magnetism to behave and how strongly it actually behaves in real experiments. That mismatch is not a mistake or an experimental error. It is a real, measured signature of this flickering cloud interfering with the electron's magnetism, and untangling that mismatch became one of the most demanding measurement projects modern physics has ever attempted. Every electron acts like an incredibly small magnet, a property tied directly to what physicists call its spin. Early calculations, using the simplest possible version of quantum theory, predicted a precise value for exactly how strong that tiny magnet should be. Real experiments measured the electron's actual magnetic strength and found something slightly different, off from the simple prediction by a tiny fraction, far too small to notice in daily life, yet far too large to ignore inside careful physics. That small mismatch is called the anomalous magnetic moment, an intimidating name attached to a fairly graspable idea. The electron's magnetism is very slightly stronger than the simplest theory predicted, and that tiny extra strength comes directly from the swarming cloud of flickering virtual particles surrounding every electron, constantly nudging its magnetic behavior away from the clean, simple prediction. A comparison worth picturing involves a spinning top that should, according to a basic calculation, wobble at one exact predictable rate. Now imagine that top spinning inside a room filled with a constant chaotic breeze brushing against it from every direction, nudging its wobble very slightly away from that clean predicted rate. The electron's magnetism experiences something similar, constantly nudged by the storm of virtual particles surrounding it, producing a magnetic strength slightly different from the simplest possible prediction. This mismatch is astonishingly tiny, showing up only after measuring the electron's magnetism out to an extraordinary number of decimal places. Yet physicists did not shrug off a difference that small. They chased it down with extreme precision, because a mismatch this small, appearing consistently and reliably across repeated experiments, carries enormous meaning about how completely physicists actually understand the electron. Calculating a predicted value for this tiny mismatch required accounting for the effects of that entire swarming cloud of virtual particles, an enormously complicated calculation involving countless possible ways those flickering particles could interact with the electron. Physicists spent decades refining that calculation, adding layer after layer of complexity to account for increasingly rare and subtle interactions happening inside that flickering cloud. When the final predicted number was compared against the number measured directly in the lab, the match was staggering, correct to roughly 10 decimal places, an agreement between theory and experiment considered one of the most precise matches in the entire history of science. That level of agreement is often compared to predicting the exact distance between two cities and matching it correctly down to the width of a single human hair. This staggering precision did not come cheap. Measuring the electron's magnetism to that level of accuracy and calculating a matching prediction from theory ranks among the most demanding, expensive, and time-consuming projects modern physics has ever attempted, stretching across decades of careful work and costing enormous amounts of money and effort. Exactly how physicists pulled off a measurement that precise, trapping a single electron almost perfectly still inside a laboratory for months at a time, is where this story heads next. Measuring an electron's magnetism to an extraordinary number of decimal places required physicists to do something that sounds nearly impossible. They needed to trap a single electron, completely isolated from every other particle in the universe, holding it almost perfectly still inside a laboratory for weeks or even months at a time, watching it wobble with the patience and precision of an engineer inspecting the finest machinery ever built. The device physicists eventually built for this task is sometimes nicknamed a particle trap, using powerful magnetic fields to hold a single electron suspended in place inside an extremely cold chamber, shielded as thoroughly as possible from any outside disturbance that might throw off the measurement. Cooling the chamber down close to the coldest temperature theoretically possible reduces random jittering that would otherwise blur the measurement beyond usefulness. A comparison worth picturing involves trying to measure the exact wobble of a single spinning coin balanced on its edge, inside a room shielded from every gust of wind, every vibration from passing traffic, and every stray sound wave, then watching that coin for months without a single interruption, recording its wobble with tools sensitive enough to detect the smallest possible shift. That level of isolation and patience is roughly what physicists needed to pull off this measurement successfully. This project required decades of refinement, with each new generation of the experiment squeezing out another decimal place of precision, an achievement that demanded enormously expensive equipment, some of the most sensitive detectors ever constructed, and research teams dedicating entire careers to a single, incredibly precise number. Funding a project this demanding required convincing governments and universities that a number this small could genuinely matter. Here is why that tiny number carries such enormous weight. This measurement of the electron's magnetism stands as one of the most rigorously tested predictions in the entire history of science, confirmed to a level of precision matched by almost nothing else humans have ever measured. If the underlying theory describing electrons and their flickering cloud of virtual particles were even slightly wrong, this measurement would have caught the mistake immediately, since even a tiny deviation would show up clearly at this level of precision. Because that mismatch matched theory so precisely, this measurement became one of physics' strongest confirmations that the framework describing electrons, called quantum electrodynamics, correctly captures how electrons truly behave at the smallest scales tested so far. Some physicists consider it the single most successful, most precisely verified prediction that human science has ever produced. Yet even with a match this precise, deep questions about the electron remain wide open. This staggering agreement confirms how the electron behaves under the flickering cloud surrounding it, without ever explaining what the electron fundamentally is underneath all of that activity. That deeper question, whether the electron is a truly solid, indivisible point, or whether smaller pieces are hiding inside it waiting to be discovered, has driven physicists to build some of the largest and most powerful machines ever constructed, hunting for a crack inside the electron that, so far, has never once appeared. For most of scientific history, every particle eventually cracked open to reveal something smaller hiding underneath. Atoms were once believed to be the smallest possible pieces of matter, until scientists discovered protons, neutrons, and electrons hiding inside them. Protons and neutrons themselves seemed solid, until scientists found even tinier particles called quarks swirling inside them, held together by forces stronger than anything else known in physics. Given that repeated pattern, many physicists naturally suspected the electron might follow the exact same path, eventually revealing smaller building blocks hiding inside it once scientists built machines powerful enough to look closely enough. Scientists even gave a name to these hypothetical smaller pieces before finding a shred of evidence for them, calling them preons, imagining tiny building blocks that might combine in different arrangements to produce electrons, quarks, and every other basic particle known to physics. A comparison worth picturing involves Russian nesting dolls, the wooden toys where opening one doll reveals a smaller doll hiding inside, which opens to reveal an even smaller doll, continuing downward through several layers. Atoms, protons, and quarks followed exactly that nesting pattern, layer after layer, each one cracking open to reveal something smaller. Scientists naturally expected the electron to be just another doll in that same nested sequence, assuming smaller building blocks were waiting to be found inside. The prion idea offered physicists an appealing possibility, a way to explain patterns that otherwise look like pure coincidence, such as why electrons, quarks, and other basic particles share certain mathematical similarities in their properties. If all of these particles were built from the same small set of even tinier building blocks, arranged in different combinations, those shared similarities would make far more natural sense than treating each particle as a completely separate, unconnected building block of nature. Several different prion models were proposed across the decades following this idea's introduction, each one attempting to explain how a handful of hypothetical smaller particles might combine to recreate every particle physicists had already discovered, including the electron. Some models proposed just 2 or 3 types of prions. Others proposed more elaborate combinations, each with its own predictions about what evidence should eventually turn up if the idea were correct. None of those predictions have ever been confirmed. Every single experiment designed to detect a crack inside the electron, a sign of internal structure, a hint of smaller pieces rattling around inside, has come back completely empty, showing an electron behaving exactly like a single, solid, indivisible point every single time, no matter how powerful the equipment used to search. That repeated, consistent failure to find anything smaller inside the electron has not ended the search. Physicists have instead built increasingly powerful machines specifically designed to smash particles together with enough force to crack open even the tightest, smallest possible hiding spot, and exactly how close those machines have managed to look, and exactly how small a hiding spot they have ruled out completely, is where the hunt continues next. Finding smaller particles hiding inside something requires smashing that something apart with enormous force, then carefully studying the wreckage for clues about what pieces were hiding inside before the collision. That is precisely how scientists discovered quarks hiding inside protons decades ago, firing high-energy particles into protons and watching how they scattered, a pattern that only made sense if smaller, harder pieces were buried inside. Scientists applied that exact same strategy to the electron, using massive machines called particle colliders, accelerating electrons to speeds extremely close to the speed of light, before smashing them into other particles with tremendous force. If the electron contained smaller pieces hiding inside it, similar to how protons contained quarks, that collision should scatter in a telltale pattern, revealing evidence of that internal structure. Every single test has come back completely empty. The electron scatters exactly the way a genuinely solid, structureless point would scatter, with absolutely no sign of anything smaller rattling around inside. Physicists have run this test using some of the most powerful particle accelerators ever constructed, including massive underground rings stretching across entire countries, and the result has never once changed. A comparison worth picturing involves smashing a sealed cardboard box against a wall as hard as possible, expecting the wreckage to reveal smaller objects hidden inside, only to find the box behaved as though nothing at all were packed inside it, every single time you tried, no matter how hard you threw it or how many boxes you tested. That is roughly the situation physicists find themselves in with the electron, a consistently empty result despite repeated forceful attempts to crack it open. This repeated failure to find anything smaller does not necessarily mean nothing is hiding inside the electron. It means that if something is hiding inside, it must be tucked away at a scale far smaller than even the most powerful machines built so far can detect, hidden behind a wall of tininess that current technology simply cannot punch through yet. Some physicists take this repeated empty result as strong evidence that the electron truly is exactly what it appears to be, a genuinely fundamental particle with no smaller pieces hiding inside it at all, closing the book on the prion idea as an interesting guess that nature simply did not choose to use. Other physicists remain cautious, pointing out that every previous particle once assumed to be fundamental, including the atom itself, eventually revealed hidden structure once technology finally caught up to the challenge. This ongoing hunt has produced one genuinely useful result regardless of which side turns out to be correct. Even without finding anything smaller inside the electron, these repeated collision experiments have allowed physicists to calculate an upper limit on how large any hidden structure inside the electron could possibly be, squeezing that hypothetical hiding spot down to a size almost too small to imagine, a size that makes even a single proton look impossibly gigantic by comparison, and reaching that number is exactly where the story goes next. Physicists cannot prove the electron has absolutely zero size, since proving a true zero requires testing every possible scale down to infinity, an impossible task for any machine. What physicists can do instead is calculate an upper limit, a largest possible size the electron could have, while still matching every single experiment ever run without producing a detectable difference from a true sizeless point. That upper limit is almost impossible to picture using ordinary comparisons. A single proton, already far too small to see even with the strongest optical microscope ever built, is roughly 100,000 times smaller than a single hydrogen atom. Current experiments show that if the electron has any size at all, that size must be at least 10,000 times smaller than a proton, and likely far smaller still. Here is a comparison worth stretching your imagination around. If a proton were somehow blown up to the size of the entire planet Earth, any hidden structure inside an electron would still be smaller than a single football field sitting somewhere on that planet-sized proton. That comparison barely captures how extreme this size limit actually is, since real experiments push the limit even further than that single example suggests. This extreme limit comes from an experiment called measuring the electron's magnetism to an extraordinary number of decimal places, the very same measurement that took decades and enormous resources to pull off. Any hidden internal structure inside the electron would very slightly disturb that magnetism, in a way sensitive enough instruments would eventually detect. Because the measured magnetism matches the prediction for a truly sizeless point so precisely, physicists can calculate exactly how large any undetected structure could possibly be, while still hiding successfully within that tiny margin of agreement. Reaching this level of precision required combining results from multiple different types of experiments, including particle collisions, precise magnetism measurements, and careful studies of how electrons scatter off other particles at extremely high energies. Each different type of experiment placed its own separate limit on the electron's possible size, and physicists combined those results together to arrive at the tightest overall limit currently accepted. This number keeps shrinking every few years as technology improves, as physicists build more sensitive detectors, more powerful colliders, and more precise magnetism traps. Every improvement pushes the size limit smaller and smaller, and so far, not a single improvement has revealed any actual structure hiding inside. The electron keeps passing every increasingly difficult test thrown at it, behaving exactly like a true, structureless point every single time. This raises an unsettling question that connects directly back to where this story began. If the electron truly has zero size, a perfect mathematical point carrying real mass and real charge, then how can something with literally no size at all still be doing something physically, some kind of motion happening at the smallest possible scale? According to one strange and rarely discussed prediction buried inside the electron's own equations, a perfectly still electron might actually be trembling constantly, vibrating in place at a staggering rate that no experiment has ever managed to observe directly. And that hidden trembling is exactly where the story turns next. An electron sitting completely still, with no outside force acting on it, should be about as simple and motionless as physics gets. Yet buried inside one of the most respected equations describing the electron, developed by physicist Paul Dirac, sits a bizarre prediction. Even a perfectly still, undisturbed electron should be constantly trembling, vibrating back and forth at an almost unimaginable rate, a motion physicists nicknamed Zitterbewegung, a word borrowed from German that roughly translates to trembling motion. This predicted trembling is not gentle. According to the math, an electron sitting still would still be shaking back and forth at a rate faster than anything else known in physics, vibrating roughly 1,000,000 billion times every single second, a rate so extreme it becomes almost meaningless to picture directly using ordinary comparisons. Here is a comparison worth attempting anyway. Imagine a guitar string vibrating so fast that within the time it takes you to blink once, it has already completed more vibrations than there are grains of sand on every beach on Earth combined. That absurd rate barely scratches the surface of how fast this predicted trembling motion is supposed to happen inside a supposedly still electron. This trembling motion emerges directly from combining quantum physics with Einstein's theory of relativity inside a single equation, the same equation that first predicted the electron's antimatter twin, a discovery covered soon. The trembling appears to come from the electron's motion constantly interfering with itself, a side effect of describing a particle using both quantum wave behavior and relativistic speed limits simultaneously within the same mathematical framework. Despite being predicted by an equation trusted deeply throughout modern physics, this trembling motion has never been directly observed happening to a real, free electron floating in space. The vibration is predicted to happen at such an incredibly tiny scale and such an incredibly rapid rate that no instrument built so far comes anywhere close to being fast or precise enough to catch it directly in action. Scientists have managed something close to an indirect confirmation. However, using a completely different setup, researchers built an artificial system using trapped ions, cooled and controlled with lasers, engineered specifically to behave mathematically similar to how Dirac's equation describes an electron. Inside that artificial stand-in system, researchers successfully observed a trembling motion matching the mathematical pattern predicted for a real electron, offering indirect but genuinely encouraging evidence that the underlying prediction reflects something real about how these particles actually behave. Whether a genuine, isolated electron truly trembles this way in ordinary empty space remains formally unconfirmed by direct observation, sitting in an unusual scientific position, trusted deeply because of the equation's overall success elsewhere, yet never caught in the act for a real solitary electron. That gap between trusted math and missing direct proof echoes throughout electron physics, and it becomes even stranger with the next discovery, because the very same equation predicting this hidden trembling also predicted something even more shocking. A mirror universe worth of antimatter hiding inside the mathematics, describing the ordinary electron sitting in your own body right now. Physicist Paul Dirac set out in the late 1920s, trying to solve a specific technical problem, combining quantum mechanics with Einstein's theory of relativity into a single equation capable of correctly describing the electron. Earlier equations handled slow-moving electrons well enough, but broke down for electrons moving close to the speed of light. Dirac wanted one equation that worked at any speed. After months of work, Dirac produced an equation that succeeded brilliantly, correctly describing the electron's behavior at any speed, and even predicting the electron's spin and magnetism as a natural side effect of the math, rather than something bolted on afterward. That success alone would have secured Dirac's place in physics history. But his equation carried an extra feature nobody had asked for and nobody initially wanted. The equation produced two separate solutions for every single electron. One solution described an ordinary electron, carrying negative charge and positive energy, matching everything already known from experiments. The second solution described something that looked almost identical, same mass, same spin, yet carrying positive charge and, more troubling still, negative energy, a concept that made no obvious physical sense at the time. A comparison worth picturing involves solving a math problem asking how fast a ball must be thrown to reach a certain height, and getting two valid answers back, one positive and sensible, matching a ball thrown upward normally, and one negative, technically valid within the math, yet seemingly describing a ball falling upward out of the ground. Most people would toss out the second answer as a mathematical fluke with no real meaning. Dirac, after wrestling with the problem, chose not to. Dirac eventually proposed a strange picture to make sense of that second solution, imagining an entire infinite sea of these negative energy states filling all of empty space, invisible because every single slot in that sea was already completely full. Under this picture, an empty gap appearing in that hidden sea, caused by knocking one of these negative energy particles briefly out of place, would look to an outside observer exactly like a new particle, carrying positive charge and ordinary positive energy, essentially a mirror twin of the electron. That mirror twin needed to share the electron's exact mass, while carrying the opposite electric charge, a specific testable prediction rather than a vague guess. Many physicists at the time, including some of Dirac's own colleagues, doubted this predicted particle could be real, suspecting it was simply an artifact of flawed mathematics rather than a genuine feature of nature waiting to be discovered. Dirac's equation had accidentally revealed the theoretical existence of antimatter years before anyone had ever detected a trace of it in a real laboratory, hidden inside pure mathematics describing something as ordinary as the electron sitting in every atom around you. Whether nature actually contained this bizarre mirror particle remained completely unknown, a purely theoretical prediction waiting for confirmation, until a physicist studying particles raining down from outer space captured something in a detector that nobody expected to see, and that discovery is exactly where the story turns next. In 1932, physicist Carl Anderson was studying cosmic rays, high-energy particles constantly raining down onto Earth from outer space, using a device called a cloud chamber that made the tracks of passing particles visible as thin trails of fog, similar to the trail a jet leaves across the sky. A strong magnetic field placed around the chamber bent those trails, curving negatively charged particles one direction and positively charged particles the other. Anderson noticed a particle track that matched an electron's mass and behaviour in every way except one glaring detail. The track curved in the exact opposite direction. An electron's track should curve inside that magnetic field, meaning the particle carried positive charge rather than negative charge. Anderson had captured direct evidence of exactly the mirror particle Dirac's equation had predicted years earlier, a particle later named the positron. This discovery confirmed one of the strangest predictions physics had ever produced, turning Dirac's mathematical curiosity into a genuinely real particle, detected, measured, and photographed. Antimatter stopped being a theoretical possibility and became a confirmed feature of the universe, opening an entirely new category of matter that nobody had known to search for before Dirac's equation pointed the way. Here is what happens when an electron and a positron meet. Rather than simply colliding and bouncing apart the way two ordinary particles might, they annihilate each other completely, both particles vanishing entirely, their combined mass converting fully into pure energy in the form of a burst of light, following the same relationship Einstein described between mass and energy. Nothing physical remains of either particle afterward, only a flash of radiation carrying away everything they used to be. A comparison worth picturing involves two identical twins running toward each other from opposite directions, and instead of colliding and falling down, both twins simply vanish completely the instant they touch, releasing a bright flash of light carrying away everything they were made of. That total, complete conversion from matter into pure energy has no everyday equivalent, since ordinary collisions leave debris behind, while this leaves nothing but light. This exact process, an electron colliding with a positron and vanishing into a burst of energy, has become genuinely useful technology rather than staying locked inside physics laboratories. Hospitals around the world use a medical scanning technique built entirely around this annihilation process, injecting a patient with a substance that releases positrons inside the body, then detecting the flashes of light produced when those positrons meet electrons naturally present in the patient's tissue, building a detailed image used to spot cancer and study brain activity. Antimatter remains rare and difficult to produce in large amounts, and current technology cannot store it safely for long periods, since even a tiny amount of ordinary matter touching it triggers the same complete annihilation. What began as a strange, doubted footnote inside Dirac's equation turned into confirmed physics, real medical technology, and proof that electrons carry a hidden mirror image built directly into the mathematics describing them. That same mathematics also predicted something else strange about the electron, a rotating property called spin, and the surprising part is that the electron does not appear to be spinning at all in any ordinary sense of that word. Every electron carries a property physicists call spin, and every textbook description of an electron treats spin as one of its basic defining features, alongside mass and charge. The name suggests something simple, a tiny ball rotating on its axis like a planet or a top. That simple picture, appealing as it sounds, turns out to be flatly wrong, and physicists have known it was wrong since almost the moment the idea was proposed. Spin was introduced in 1925 by physicists George Uhlenbeck and Samuel Gaudsmit, trying to explain an experimental result from a few years earlier, an experiment where a beam of silver atoms passed through a magnetic field and split cleanly into two separate beams, instead of spreading out smoothly, as if each atom carried a tiny built-in magnet pointing in one of exactly two possible directions. Proposing that electrons literally spin on an axis, generating a magnetic effect the same way a spinning charged ball would, offered a tidy explanation. The problem appeared almost immediately once other physicists checked the math carefully. If an electron truly has zero size, as every experiment continues to confirm, spinning it fast enough to produce the magnetic strength actually observed would require its outer surface to move many times faster than the speed of light, an outcome flatly forbidden by Einstein's physics. A literal spinning ball explanation collapses the instant you take the electron's size, or lack of size, seriously. A comparison worth picturing involves a coin spinning on a table fast enough to produce a hum loud enough to be heard from across a football field, except the coin has been shrunk down to a size smaller than anything ever measured, meaning its edge would need to travel impossibly faster than light itself just to make that sound. Physics simply does not allow that, ruling out literal spinning as the true mechanism behind an electron spin. Despite that contradiction, physicists kept the word spin, because the underlying property behaves mathematically almost exactly like ordinary rotational motion in every equation where it appears, contributing angular momentum and magnetism in a pattern that closely mirrors what real spinning would produce without the physical spinning actually happening. Spin turned out to be an intrinsic quantum property, something built directly into what an electron fundamentally is, existing without any literal motion causing it. This intrinsic property is not a minor footnote. Spin is precisely the property responsible for the strict sharing rule covered earlier, the rule that keeps electrons from occupying the same space and ultimately keeps solid matter from collapsing in on itself. Every electron carries exactly the same fixed amount of this spin, oriented in one of exactly two possible directions relative to any given measurement. A strict quantum rule confirmed repeatedly across nearly a century of experiments. That strict two-option nature of spin becomes the doorway into one of the strangest connections ever discovered in physics. Take two electrons produced together under the right conditions, separate them by any distance imaginable, even across an entire galaxy, and measuring the spin of one instantly appears to determine the spin of the other. A connection that seems to ignore distance completely, and untangling exactly how strange that connection really is comes next. Certain physical processes can produce two electrons whose properties become linked together in a special way. A connection physicists call entanglement. Once two electrons become entangled, measuring the spin of one instantly tells you the spin of the other, even if the two electrons have been separated by an enormous distance, with no signal, no cable, and no visible connection running between them. Here is what makes this genuinely strange rather than merely clever. Before either electron gets measured, quantum physics describes both of their spins as genuinely undetermined, not simply unknown to the observer, but actually unsettled in a real physical sense, existing as a mixed possibility rather than a hidden, predetermined value waiting to be revealed. The instant one electron gets measured and its spin snaps into a definite value, the other electron's spin appears to snap into the opposite value immediately, regardless of how far away it sits. A comparison worth picturing, while admitting it stretches the truth to make the idea graspable, involves a pair of gloves. Imagine placing one glove in a box on Earth and its matching partner in a box on the Moon, without looking at either. Opening the Earth box and finding a left-hand glove instantly tells you the Moon box contains a right-hand glove. That comparison captures the instant correlation, but misses the deepest part of the mystery, because ordinary gloves are already secretly left or right before you open the box. Entangled electrons genuinely are not settled into one spin or the other until the moment of measurement, according to the tested predictions of quantum theory. This connection does not let anyone send a message faster than light, despite how tempting that possibility sounds. The outcome of each individual measurement remains completely random, and only by comparing notes afterward, using an ordinary, slower-than-light method like a phone call, can anyone confirm the strange correlation actually happened. No usable information travels between the two electrons instantly, only a shared correlation that nobody can control or send on command. Physicists have confirmed entanglement across genuinely impressive distances, including experiments linking particles across hundreds of miles using satellites, and the correlation holds up perfectly every single time, tested repeatedly under increasingly strict laboratory conditions, designed to rule out any trick or hidden signal sneaking between the particles. This strange instant connection troubled some of the greatest physicists of the 20th century, far more deeply than any experiment troubles physicists today, because when this idea first emerged from the math, it appeared to violate a core assumption most scientists held about how the universe must work, an assumption that nothing should be able to influence anything else faster than light can travel between them. One physicist in particular found this idea so uncomfortable that he tried to use it as proof that quantum mechanics itself must be broken, and his objection, along with the sharp name he gave this connection, comes next. Albert Einstein spent decades deeply uncomfortable with several core ideas inside quantum mechanics, and entanglement bothered him more than almost anything else the theory produced. In 1935, working alongside physicists Boris Podolsky and Nathan Rosen, Einstein published a paper arguing that quantum mechanics, despite its enormous success at predicting experimental results, must be an incomplete description of reality, missing some deeper layer of hidden information that a future, more complete theory would eventually uncover. Their argument centered directly on entanglement. If measuring one electron could instantly determine the state of a partner electron sitting an enormous distance away, Einstein argued, something must already be determining that outcome ahead of time, some hidden property carried along with each particle from the very beginning, simply unknown to physicists rather than genuinely random and unsettled. Anything else, Einstein argued, would require an influence travelling between the particles faster than light allows, an idea his own theory of relativity flatly forbade. Einstein famously described this apparent instant influence, using a phrase that stuck permanently to the idea, calling it spooky action at a distance, a phrase dripping with the discomfort he genuinely felt toward this feature of quantum theory. Einstein preferred believing the particles secretly carried predetermined properties the entire time, information physicists simply had not yet learned how to measure directly, an idea generally described using the phrase hidden variables. A comparison worth picturing involves finding out that two friends across the country always answer a coin flip question the exact same way, every single time, without ever communicating beforehand. One natural explanation assumes they secretly agreed on an answer ahead of time before separating, a hidden variable settled in advance. A stranger explanation would require the coins themselves communicating instantly across the entire country the moment either one gets flipped. Einstein strongly preferred the first explanation, distrusting anything resembling the second. Einstein was not simply expressing a vague feeling of discomfort. He was raising a scientifically serious challenge, questioning whether quantum mechanics, despite matching experimental results perfectly, was secretly missing an entire hidden layer of reality that a more complete theory would eventually reveal, restoring a universe where influences never travel faster than light, and every outcome is secretly settled in advance. For decades, this argument remained a philosophical standoff, rather than something testable in a laboratory, since the predictions of quantum mechanics and the predictions of a hidden variable explanation looked identical in most practical situations physicists could actually test. Nobody had found an experiment capable of distinguishing which explanation was actually correct, leaving Einstein's challenge sitting unresolved for nearly 30 years after his original paper. That standoff finally broke in 1964, when physicist John Bell discovered a clever mathematical test capable of genuinely distinguishing between Einstein's hidden variable picture and the strange instant correlation quantum mechanics actually predicted, a test rigorous enough to finally settle this argument using real experiments rather than pure philosophy. And running the test against reality is exactly where the story turns next. John Bell, working in 1964, discovered something remarkable while trying to settle Einstein's decades-old objection to quantum mechanics. Bell found a way to derive a precise mathematical limit, now called Bell's inequality, describing the strongest possible correlation any hidden variable theory could ever produce between two separated particles, assuming Einstein was right that nothing travels faster than light, and every outcome is secretly settled in advance. Bell then compared that strict limit against what quantum mechanics itself actually predicted for entangled particles and found something startling. Quantum mechanics predicted correlations stronger than that limit allowed, a difference small but genuinely measurable, meaning Einstein's hidden variable picture and quantum mechanics' actual predictions were no longer philosophically identical twins. They had become two rival, testable predictions, capable of being told apart using a real experiment for the very first time. Physicist John Clauser ran early versions of this test during the 1970s, followed by physicist Alain Aspect running significantly improved versions during the 1980s, closing several technical loopholes that skeptics worried might secretly explain away the results. Decades later, physicist Anton Zeilinger led experiments that closed nearly every remaining loophole, producing results considered essentially airtight by the physics community. Every single one of these experiments found the same result. The correlations between entangled particles violated Bell's inequality, exceeding the strict limit any hidden variable theory could ever produce, matching instead the stronger correlation quantum mechanics had predicted all along. Einstein's preferred explanation, a universe secretly settled in advance with no instant influences whatsoever, did not match what nature actually does. A comparison worth picturing involves a strict rule stating that no student could possibly answer a surprise pop quiz correctly more than 70% of the time purely by guessing intelligently based on hints gathered beforehand. If an entire class somehow scored 90% correct on that same quiz, every single time it was given, something beyond ordinary guessing would clearly need explaining. Bell's inequality worked the same way, setting a strict ceiling that hidden variables could never cross, a ceiling entangled particles crossed anyway over and over in experiment after experiment. This result did not mean Einstein was a poor physicist, and every scientist studying this topic today still deeply respects the seriousness of the challenge he raised. It meant that one specific cherished assumption about how reality must work, that every property is secretly settled in advance without any deeper connection between separated particles, does not hold up against how the universe actually behaves at this scale. In 2022, the Nobel Prize in Physics was awarded jointly to Clauser, Aspect and Zeilinger for this exact body of work, closing Einstein's decades-old challenge with confirmed, repeatable, loophole-free experimental proof. Entanglement stands today as genuinely real, tested physics rather than a philosophical puzzle. That same electron capable of this strange instant connection across any distance behaves completely differently when trillions of its identical copies get crushed together inside a dying star, where a rule covered earlier becomes the only thing standing between a stellar corpse and total collapse. Stars like the Sun spend most of their lives balancing two competing forces. Gravity constantly pulls every particle inward, trying to crush the star down to nothing, while the intense heat and pressure produced by nuclear fusion in the core pushes outward, holding the star's enormous size steady for billions of years. Eventually, every star runs out of fuel for that fusion process, and when that happens, gravity finally gets the upper hand. For a star roughly the size of the Sun, running out of fuel triggers a dramatic collapse, the outer layers puffing outward and drifting away into space, while the core crushes inward under gravity, with nothing left to hold it up through fusion. As that core collapses, its atoms get squeezed together with tremendous force, packing electrons closer and closer together into an incredibly small, dense space. Here is where a rule covered earlier becomes the difference between total collapse and a stable, if bizarre, dead star. Electrons, forbidden from sharing the same state in the same place, resist being squeezed any closer together once they are packed tightly enough, generating an outward pushing force strong enough to halt the collapse completely, even against the crushing pull of the star's own gravity. The collapsing core stops shrinking, settling into a strange, stable object called a white dwarf. A comparison worth picturing involves an entire object with roughly the same mass as the Sun, containing every planet's worth of material the Sun could ever hold, crushed down until it fits inside a sphere roughly the size of planet Earth. A teaspoon of material scooped from inside a white dwarf would weigh roughly as much as a fully loaded pickup truck, an almost impossible density held together entirely by the stubborn refusal of electrons to occupy the same space. This process happens to the vast majority of stars in the universe, including billions of years from now, our own Sun, which will eventually shrink down into a white dwarf roughly the size of Earth after it exhausts its own fuel supply. White dwarfs are common, confirmed objects, observed directly by astronomers using powerful telescopes, their extreme density calculated through careful measurements of their gravity and their light. What holds a white dwarf up against total collapse is not heat, not ordinary gas pressure, and not any force resembling anything you would encounter in daily life. It comes entirely from a quantum rule governing electrons, the exact same rule keeping you from falling through your chair, scaled up to hold together an entire dead star weighing as much as the sun. This pressure produced by tightly packed electrons behaves nothing like the pressure inside a balloon or a car tire, and understanding exactly why it works the way it does, completely independent of temperature, reveals one of the strangest forces in all of physics, a force with genuinely no equivalent anywhere in classical everyday explanations of how pressure and pushing normally work. Ordinary pressure, the kind pushing outward inside a balloon or a car tire, comes from countless tiny particles bouncing around and colliding with their container, driven by heat. Cool that balloon down enough, removing essentially all the heat energy from the particles inside, and the pressure would eventually drop toward nothing, since the particles would stop moving and stop bouncing off the walls. The pressure holding up a white dwarf star works completely differently, and this difference is exactly what makes it so strange. Even if you could somehow cool a white dwarf's crushed core down to the coldest temperature theoretically possible, removing every last trace of heat, the electrons packed inside would still push back against further compression with tremendous force. This pressure has genuinely nothing to do with heat or temperature. The real source of this pressure comes directly from the same strict sharing rule covered earlier. As electrons get squeezed into an increasingly small space, that rule forbids them from settling into the same low energy state together, forcing them instead to stack upward into increasingly higher energy states, filling up available slots the same way people fill up seats in a movie theatre, from the front row backward once the front rows are taken. Electrons forced into higher energy states move faster, and that increased motion produces real, physical pressure pushing outward, entirely independent of temperature. A comparison worth picturing involves a crowded elevator that refuses to let more than one person occupy any single square foot of floor space, no matter how badly everyone wants to squeeze closer together. As more people pack into that elevator, they get pushed higher and higher, some practically forced to stand on tiptoes or lean awkwardly against the ceiling, purely because the floor space rule leaves nowhere else for them to go. That forced upward stacking, not heat, is roughly what generates the pressure holding a white dwarf star together. This purely quantum pressure has a genuine limit, however, one calculated precisely by physicist Subrahmanyan Chandrasekhar in the 1930s. If a stellar core's mass exceeds roughly 1.5 times the mass of the Sun, even this stubborn electron pressure cannot hold back gravity any longer. Electrons get forced to combine directly with protons, transforming into neutrons, and the collapse continues even further, crushing the star down into an object called a neutron star, or in the most extreme cases into a black hole. Chandrasekhar's calculation has been confirmed repeatedly through astronomical observations, matching the masses of white dwarf stars found scattered throughout the galaxy with remarkable precision. This limit stands today as one of the most solid, well-tested predictions in all of astrophysics, marking the exact boundary where even the electron's stubborn refusal to share space finally runs out of strength against the crushing pull of gravity. Electrons pushing back an entire collapsing star is strange enough on its own, but electrons can behave just as bizarrely under far gentler conditions, inside ordinary materials sitting quietly in laboratories right here on Earth, where certain carbon-based structures force electrons to move as though they carry no mass whatsoever, a discovery that traces directly back to the same element that forms one of the hardest, most familiar materials on the planet. Carbon is one of the most familiar elements on Earth, forming diamond, the hardest naturally occurring material known, where carbon atoms bond into a rigid three-dimensional lattice, locking every atom firmly in place. That same element, arranged in a completely different pattern, produces something startlingly different. A single, flat sheet of carbon atoms, only one atom thick, arranged in a hexagonal pattern resembling chicken wire, called graphene. Inside graphene, electrons behave in a way that stunned physicists once the material was finally isolated and studied carefully in the laboratory. Electrons moving through this thin carbon sheet act as though they carry zero mass, obeying equations closely resembling the same relativistic equations Paul Dirac originally developed to describe electrons moving near light speed, except here that behavior emerges from an ordinary material sitting on a lab bench rather than from deep space or a particle accelerator. Here is why that behavior counts as genuinely strange. An electron travelling freely through empty space carries a small but very real mass, confirmed through countless precise measurements. Inside graphene, the surrounding arrangement of carbon atoms changes how electrons move through the material so dramatically that they behave mathematically identical to massless particles, while confined inside that sheet, reaching speeds inside the material that, while still slower than true light speed, are remarkably fast compared to how electrons typically move through ordinary materials like copper wire. A comparison worth picturing involves running normally on solid ground, then stepping onto a surface so perfectly smooth and specially designed that your legs suddenly move as though gravity barely affects you at all, letting you glide forward far faster and more effortlessly than running should ever allow, purely because of the surface you happen to be standing on, rather than any change to your actual body. Graphene does something similar to electrons, dramatically altering their effective behavior purely through the surrounding atomic arrangement. Physicists Andrei Geim and Konstantin Novoselov first successfully isolated graphene in 2004, using a surprisingly simple method involving ordinary sticky tape repeatedly pressed against a block of graphite to peel away single atom-thick layers. That discovery earned them the Nobel Prize in Physics in 2010, and it opened up an entirely new field studying how electrons behave inside similar carefully engineered flat materials. This massless behavior has been confirmed repeatedly through direct laboratory measurements, including experiments studying how graphene conducts electricity and how it responds to magnetic fields, both producing signatures that only make sense if electrons inside the material truly are behaving as effectively massless particles. This is confirmed, tested physics rather than a theoretical guess, even though it initially sounds like pure science fiction. Graphene is far from the only material capable of bending an electron's ordinary behavior into something unrecognizable. Certain other specially engineered materials push electrons even further, allowing them to flow with absolutely no resistance whatsoever, gliding through the material as though an invisible force like friction or even gravity itself simply does not apply to them anymore, and that even stranger material behavior is exactly where the story heads next. Push an electric current through an ordinary wire, like the copper wiring inside your house, and some of that electrical energy always gets lost along the way, converted into heat as electrons collide repeatedly with atoms inside the metal, bumping and scattering constantly as they struggle to move forward. That constant collision and energy loss is called electrical resistance, and it happens inside every ordinary conductor you have ever encountered. Certain special materials, when cooled down below a specific critical temperature, undergo a dramatic transformation called superconductivity, where electrical resistance does not simply decrease. It vanishes completely, dropping to exactly zero. Electric current flowing through a superconducting material can theoretically keep flowing forever, without losing any energy whatsoever, a behavior confirmed directly in laboratory experiments where currents have been observed circulating inside superconducting loops continuously for years without any detectable decay. The explanation behind this behavior involves electrons doing something they normally refuse to do, briefly pairing up with each other despite their natural tendency to repel due to sharing the same negative charge. Inside a superconductor, subtle vibrations rippling through the material's atomic structure create a faint attraction pulling certain electrons into loosely bound pairs, called Cooper pairs, named after physicist Leon Cooper, who helped develop the theory explaining exactly how and why this pairing happens. These paired electrons move through the material in a highly coordinated, almost choreographed fashion, avoiding the random scattering and bumping that causes ordinary electrical resistance. A comparison worth picturing involves a massive, chaotic crowd of people trying to cross a busy street individually, constantly bumping shoulders and slowing each other down, compared to that same crowd suddenly moving together in perfectly synchronized rows, gliding across the street without a single collision, moving as one coordinated unit rather than a chaotic mob. Superconductivity is not a rare laboratory curiosity confined to physics textbooks. It already powers real technology used every single day. Magnetic resonance imaging machines found in hospitals rely on powerful superconducting magnets to generate the strong, stable magnetic fields needed to produce detailed images of the human body. Certain experimental high-speed trains use superconducting magnets to float above their tracks using magnetic levitation, eliminating friction between the train and the rail entirely. Most confirmed superconductors currently require extremely cold temperatures to function, often colder than outer space itself, a practical limitation that has driven decades of research searching for materials capable of superconducting at warmer, more practical temperatures. Scientists have made genuine progress, discovering materials that superconduct at increasingly higher temperatures, though a material capable of superconducting comfortably at ordinary room temperature under normal pressure remains an actively pursued, unconfirmed goal rather than a finished achievement. From holding up dying stars to flowing forever without resistance, electrons keep revealing behavior that has genuinely reshaped modern technology and modern physics alike. Every single one of these behaviors, no matter how strange, ultimately traces back to the same tiny, sizeless particle, responsible for something even more fundamental, something so basic it easily gets overlooked. The simple fact that every chemical bond holding every molecule on Earth together depends entirely on electrons behaving in ways science still cannot fully explain from first principles. Every molecule in existence, from the water filling your glass to the proteins folded inside your own cells, holds together because of chemical bonds, and every single chemical bond, without exception, is fundamentally a story about electrons. Atoms bond together by sharing electrons, transferring electrons, or pooling electrons together into a shared flowing sea, and the specific way electrons behave in each situation determines nearly every property the resulting material ends up having. Carbon atoms bonding into diamond, sharing electrons in a rigid three-dimensional pattern, produces the hardest naturally occurring material on Earth. Those same carbon atoms bonding into flat, stacked sheets instead, sharing electrons in a completely different pattern, produces graphite, soft enough to write with on paper. Identical atoms, identical particles involved, yet dramatically different materials, purely because of how the electrons connecting those atoms are arranged. Salt dissolves in water because water molecules use their own arrangement of electrons to pull apart the electron-based bonds, holding sodium and chlorine atoms together inside a salt crystal. Metal conducts electricity easily because metal atoms release some of their outer electrons into a shared, freely moving pool, letting an electric current flow smoothly through the material. Wood does not conduct electricity nearly as well, because its atoms hold their electrons far more tightly, refusing to release them into a similar shared pool. A comparison worth picturing involves an entire city's transportation system built around exactly one type of vehicle, and depending on how that single vehicle type gets organized, arranged, and shared between different neighborhoods, the resulting city could end up looking like anything from a rigid grid of skyscrapers to a sprawling, loosely connected suburb. Electrons function similarly, a single basic type of particle whose different arrangements between atoms produce the entire staggering variety of materials filling the world around you. Chemists and physicists have become remarkably good at predicting electron behavior inside molecules, using powerful computer simulations to model how electrons will arrange themselves around new molecular structures before those molecules are ever built inside a real laboratory. This predictive power has become genuinely essential to modern science, helping researchers design new medicines, new materials, and new technologies, built almost entirely around anticipating how electrons will behave once atoms get arranged in a particular pattern. Here lies a genuinely strange contradiction sitting at the heart of modern science. Researchers can predict, with extraordinary accuracy, exactly how electrons will behave inside almost any molecule imaginable, confirmed repeatedly by comparing those predictions against real laboratory results. Yet despite that remarkable predictive mastery, the deepest question about what an electron fundamentally is, a sizeless point, a spread-out wave, or something science has not yet found the right words to describe, remains genuinely unresolved after nearly a century of dedicated research. This same gap between confident prediction and deep uncertainty extends even to the electron's most basic property, its electric charge, a number locked into every single electron with perfect, unchanging precision, and one that no existing theory can actually explain or predict from any deeper principle, a mystery worth examining closely next. Every electron in the universe carries exactly the same electric charge, a fixed, unchanging value confirmed through some of the most precise measurements science has ever performed. This number shows up constantly throughout physics, appearing in equations describing everything from simple static electricity to the most advanced particle physics experiments ever conducted, and every single measurement ever taken agrees with every other measurement to an extraordinary number of decimal places. Here is the puzzling part. Despite how central this number is to nearly every branch of physics, no existing theory actually explains why the electron's charge has the specific value it has, rather than some other value entirely. Physicists must simply measure this number directly through experiments, and then plug that measured value into their equations by hand, treating it as a basic, unexplained input rather than something derived from a deeper underlying principle. A comparison worth picturing involves a recipe for a cake that works perfectly every single time, producing an identical, delicious result no matter who bakes it or where. Yet nobody involved in writing that recipe can explain why the exact amount of sugar listed happens to be the correct amount. Only that decades of careful testing confirm it always works out precisely that way. Physics treats the electron's charge in a remarkably similar fashion, a number confirmed repeatedly through testing, without any deeper explanation for why that specific number was chosen by nature. This is not simply a case of physicists failing to look hard enough. Many of the most successful theories in physics, including the framework called the Standard Model that describes nearly every known particle and force, require researchers to measure this charge value experimentally and insert it directly into the theory as a starting ingredient. The theory works beautifully once that number gets included, correctly predicting an enormous range of experimental results, yet the theory itself offers no explanation for where that particular number originally came from. Some physicists suspect a deeper, more complete theory of physics, one that has not yet been discovered, might eventually explain this number naturally, deriving the electron's charge from some more fundamental principle, the same way certain other numbers in physics can already be calculated from deeper theories, rather than simply measured by hand. Other physicists remain genuinely uncertain whether such a deeper explanation exists at all, wondering if this number might simply be a basic, unexplainable fact built directly into the fabric of reality itself. This uncertainty has not stopped physicists from using the number with complete confidence throughout modern technology and modern research. Every calculation involving electric circuits, chemical bonds, or particle physics experiments relies on this exact charge value, confirmed and reconfirmed through immense amounts of testing, even while the deeper question of why nature chose this specific number remains genuinely open. This open question carries weight far beyond simple curiosity, because the exact value of the electron's charge appears to matter enormously for whether a working, life-supporting universe could even exist in the first place, an idea that pushes this story from simple mystery into something approaching genuine cosmic significance. And that connection is exactly where the story turns next. The exact value of the electron's charge does more than simply appear inside equations describing electricity and chemistry. It directly shapes how atoms hold together, how strongly electrons bind to the protons inside atomic nuclei, and ultimately how stars burn, and how chemistry itself is even possible. Physicists studying this connection have noticed something worth taking seriously, that even a small shift in this fundamental number could have prevented a working complex universe from ever forming at all. If the electron's charge were noticeably stronger than the value actually measured, electrons would bind far too tightly to atomic nuclei, changing how atoms bond together and potentially preventing the kind of rich, flexible chemistry needed to build complex molecules, including the molecules necessary for life. If the charge were noticeably weaker instead, atoms might struggle to hold together at all, drifting apart too easily to form stable matter in the first place. A comparison worth picturing involves a single setting on a massive machine responsible for building every structure in an entire city, where turning that one setting even slightly in either direction causes every building constructed afterward to either collapse under its own weight or fail to hold together as a stable structure at all. The electron's charge functions similarly inside the deeper machinery of physics, a single number whose precise value appears deeply connected to whether stable structures, from atoms up to entire stars, can exist at all. This idea belongs to a broader area of physics called fine-tuning, where scientists have noticed that several basic numbers throughout physics, including the electron's charge, appear to sit within a surprisingly narrow range required for a complex, life-supporting universe to form. Some physicists interpret this narrow range as pointing toward an unanswered mystery about why these numbers landed exactly where they did. It is worth being clear about how solid this idea actually is. The fine-tuning observation itself rests on careful calculations most physicists agree are broadly correct, calculations showing that many physical constants do appear surprisingly well suited to producing a stable universe. What remains genuinely debated, however, is the deeper explanation behind that apparent fine-tuning. Some physicists suspect an enormous number of different universes exist beyond our own, each with different physical constants, and we simply find ourselves inside one of the rare universes where the numbers happen to work out favourably. Others suspect a deeper, still undiscovered theory of physics might eventually explain why these specific numbers were essentially required rather than randomly chosen. This remains one of the most actively debated topics at the very edge of modern physics, discussed seriously by working physicists while still lacking any confirmed, agreed-upon answer. What stays genuinely solid amid that debate is the underlying calculation itself that the electron's tiny, precise charge sits in a surprisingly narrow, seemingly important range. This same electron, whose charge appears so delicately balanced, gets its actual mass from a completely different, separately confirmed piece of physics, a discovery involving an invisible field filling the entire universe, one that finally explained where the electron's mass comes from, while leaving its own version of an unanswered question sitting quietly underneath that explanation. For decades, physicists understood clearly that particles like the electron carry real, measurable mass, without having a solid explanation for where that mass actually comes from at the deepest level. In the 1960s, physicist Peter Higgs, along with several other researchers working independently around the same time, proposed a solution involving an invisible field filling every corner of the entire universe, now called the Higgs field. According to this theory, particles gain mass by interacting with this invisible field as they move through it, similar to how an object moving through water experiences resistance slowing it down. Particles that interact strongly with the Higgs field experience strong resistance, giving them a large mass. Particles that interact weakly experience far less resistance, giving them a much smaller mass. Some particles, like the particles of light called photons, do not interact with this field at all, leaving them with no mass whatsoever. This theory remained unconfirmed for nearly 50 years, a mathematically elegant idea without direct experimental proof. That changed in 2012, when scientists working at the Large Hadron Collider, an enormous particle accelerator built underground near Geneva, Switzerland, announced the discovery of a new particle matching the properties predicted for the Higgs boson, a tiny ripple in the Higgs field itself, confirming the field's existence directly through experiment rather than through theory alone. A comparison worth picturing involves walking through a swimming pool filled with water compared to walking through an empty air-filled room. Moving through the pool takes noticeably more effort, as the water resists your motion at every step, while moving through the empty room feels effortless by comparison. The Higgs field acts something like that pool filling all of space, and particles like the electron experience a kind of resistance moving through it, resistance that shows up as the mass we measure. The discovery of the Higgs boson earned Peter Higgs, along with physicist François Englert, the Nobel Prize in Physics in 2013, cementing this explanation as confirmed, tested physics rather than a theoretical guess. The electron's mass, a number measured with extraordinary precision in laboratories around the world, now has a genuine physical explanation tracing directly back to this invisible field filling the universe. Yet even this confirmed explanation leaves a deeper question standing, one that echoes the earlier mystery surrounding the electron's charge. The Higgs field explains the mechanism producing mass, essentially describing how the electron interacts with this invisible field to gain resistance and therefore weight. It does not explain why the electron interacts with that field at exactly the specific strength it does, a strength that determines the electron's precise, measured mass. That specific interaction strength, like the electron's charge, must simply be measured and plugged into the theory by hand, without any deeper principle currently available to explain why nature chose that particular value. Every mystery covered so far involves an electron behaving strangely while still remaining, in every confirmed test, a stable, real, measurable particle. There is one final genuinely unconfirmed scenario physicists have calculated, involving what might theoretically happen if you tried compressing an electron's mass down into a space small enough to trigger the extreme physics normally reserved for the collapsed remains of dead stars. And that theoretical extreme is exactly where the story turns next. Earlier in this story, a massive dying star collapsed under its own gravity, until crushed matter formed either a white dwarf or, under extreme enough conditions, an even denser object called a black hole, a region where gravity grows so strong that nothing, not even light, can escape once it crosses a certain boundary. Physicists have calculated exactly how small and dense an object needs to become, relative to its own mass, before crossing that boundary and turning into a black hole. This raises a genuinely strange theoretical question. The electron carries real, measured mass, confirmed through decades of precise experiments. According to the same calculation used for stars, an object carrying the electron's specific mass would need to be compressed into an almost unimaginably tiny region, far smaller than even the extreme size limits already placed on the electron through collider experiments, before it would theoretically qualify as a black hole under the standard equations describing gravity. Here is where this idea runs directly into a genuine, unresolved problem sitting at the frontier of the modern physics. Calculating what happens at that scale requires combining two of physics' most successful theories: quantum mechanics, which governs the electron's strange, tiny-scale behavior, and general relativity, which governs gravity and black holes at an enormous cosmic scale. Physicists have never successfully combined these two theories into a single, complete, working framework capable of making reliable predictions at a scale this extreme, an unsolved problem researchers call the search for a theory of quantum gravity. A comparison worth picturing involves owning two separate sets of house blueprints, one describing exactly how the plumbing works throughout an entire building, and another describing exactly how the electrical wiring works throughout that same building. Each blueprint completely accurate and reliable on its own, yet with no combined blueprint showing how plumbing and electrical systems interact with each other at the exact same spot inside a wall. Physicists currently find themselves in a similar situation, trying to describe an electron crushed down to the scale where gravity and quantum behavior would both matter simultaneously. A small number of physicists have explored highly speculative mathematical models suggesting an electron might actually behave something like an extremely small, spinning black hole, built from a specific mathematical solution to Einstein's gravity equations called the Kerr-Newman solution, which describes rotating, electrically charged black holes. Under this speculative framework, some of the electron's confirmed properties, including its charge and its spin, bear an intriguing mathematical resemblance to the same properties such a tiny black hole would theoretically carry. This idea remains firmly in the category of unconfirmed, actively debated theoretical speculation, discussed by a relatively small number of physicists working at the very edge of the field, rather than an accepted mainstream explanation for what an electron truly is. No experiment has confirmed or ruled out this specific picture, and most physicists remain genuinely uncertain whether it points toward real, deeper physics or toward an interesting mathematical coincidence with no true physical meaning behind it. What stays remarkable, regardless of how this particular speculation eventually turns out, is that a particle small enough to show no detectable size in even the most powerful colliders ever built can still be seriously discussed using the same equations describing the most extreme gravitational objects known to exist in the entire universe, and that strange range, from the smallest confirmed scale in physics to the largest, sets up the final, unresolved question this entire story has been building toward. Every mystery covered across this entire story circles back to a single, unresolved question. Is the electron truly, completely fundamental, a genuine point with zero size and no internal structure whatsoever, exactly as every experiment run so far has confirmed? Or is it one undiscovered layer away from revealing something smaller hiding inside, waiting for a machine powerful enough, or a theory complete enough, to finally crack it open the way atoms, protons and neutrons were each eventually cracked open before it? Nearly a century of increasingly precise experiments has failed to find a single crack, a single hint of internal structure, a single sign that the electron is anything other than exactly what it appears to be. That consistent repeated result across generations of physicists and generations of increasingly powerful machinery counts as some of the strongest, most carefully tested evidence in the entire history of science, confirmed, repeatable, and unchanged no matter how hard scientists have pushed to break it. Yet genuine deep questions remain wide open underneath that confirmed simplicity. Nobody can currently explain why the electron's charge carries the exact value it does. Nobody can currently explain why the electron's mass, set by its interaction with the Higgs field, landed on that specific number rather than any other. Nobody has resolved what truly happens during the strange collapse from spread out wave to sharp, definite particle the instant a measurement occurs. And nobody has combined quantum physics with gravity closely enough to say with confidence what would actually happen if an electron were ever crushed down to the scale where both theories should apply at once. A comparison worth ending on involves an explorer who has mapped every visible inch of a vast cave system with flawless tested accuracy, able to predict exactly what lies around every corner already explored, while a handful of narrow passages at the very edge of that map remain completely dark, unexplored and unexplained, hinting that the full shape of the cave might still stretch far beyond anything charted so far. Physics currently stands at exactly that edge with the electron, holding a map trusted completely everywhere it has actually been tested, while several passages at the boundary remain genuinely unexplored. This single, tiny particle, carrying no detectable size, sits at the center of everything solid you have ever touched, every spark of electricity powering your devices, every chemical bond holding your own body together, and every dying star's final crushing collapse across the universe. A point with no size at all has turned out to be one of the largest unresolved questions remaining in modern physics. Whatever the electron ultimately turns out to be, a truly final indivisible point, or a doorway hiding something deeper underneath, the search to find out continues today, inside particle colliders stretching for miles underground, inside laboratories chasing ever more precise measurements, and inside the mathematics physicists are still writing, chasing an answer to a question that started with the simplest possible object anyone could imagine, and somehow became one of the deepest mysteries science has ever faced.